Okay? So our next type of interaction in terms of strength, so this was London dispersion and we just did that one. So our next type is dipole-dipole. Now, remembering that the word dipole means two poles. And from our previous chapter, that means polar, right? We need a positive pole and a negative pole, okay? So in this case, dipole-dipole interactions, this is a permanent. A permanent interaction. Okay? Because when something is polar, it's not due to a shifting of an electron cloud. It is permanently that way. So if it's polar, then you've got a permanent interaction which is stronger than a momentary one. So let's look at how this works. So water, being the best molecule ever, gives us a very good example. So from our last chapter, we learned about how to tell polarity, right? And so if you decided whether or not water was a polar molecule, you would look at the hydrogen-oxygen bond, this one right here, and you would determine that oxygen is more electronegative. And we know because water is bent, that there's a net pull in this direction. So this means a polar molecule, right? And remember, our arrow points in the direction of the negative charge. So the negative is over here, and the positive is over here, right? So let me take some of this extra stuff out. Okay. So my water molecule is a negative side here and a positive side here, okay? And this is permanent, permanently polar, okay? So let's say I have another water molecule, and it's also got, because it's water, has a positive and negative side. So because positives and negatives attract, we have an interaction between the positive side of the one water molecule and the negative side of the other. Okay? So the important thing is that in order to have dipole-dipole interactions, this must be polar molecules. Okay? That's very, very important. Must be a polar molecule. All right, so let's look at our third option for bonding, or interactions. Okay. And our next strongest of the three is what's called hydrogen bonding. Now, in order to have hydrogen bonding, you must have hydrogen bonded directly, and that's important, to an oxygen, nitrogen, or a fluorine. Okay? Now I want to clarify something before we go any further with this topic. So again, let's look at our water molecule because it's the best. So when we talk about hydrogen bonding, and we're using the term hydrogen bonding, we are not talking about this. Okay? Listen to the words that I'm saying. We are not talking about the bond between a hydrogen and an oxygen. Okay? That's not what we're using that term for. Okay? What we are talking about is the fact that this hydrogen here, or this hydrogen here, has an attraction to that oxygen because of this bond. Okay? Because we have a hydrogen bonded directly to an oxygen, this interaction here can take place. Okay? And if I had another water molecule, and I'm just going to do it in blue because I'm already in blue. If I had another one, I would have this interaction, right? And if I have another one, I have this interaction, right? So water has the ability to do dispersion forces, it has the ability to do dipole-dipole forces, and it has the ability to do hydrogen bonding. Now, anything that can do hydrogen bonding can hydrogen bond to anything else that can do hydrogen bonding. So let's say, change some color here, let's say I've got some ammonia. Right? I've got a hydrogen bonded directly to a nitrogen. So this one can do hydrogen bonding. Okay? And so I will have an interaction between my hydrogen and my nitrogen. Okay? Or if I had HF, right? Again, hydrogen bonded directly to a fluorine, I can do hydrogen bonding here. Okay? But it's very important to keep in mind, I'm going to switch to a vibrant color, that hydrogen bonding is this stuff in between things. Okay? Remember that this hydrogen bonding is the interaction between molecules. Right? All right. So, there is a process to evaluating intermolecular forces. Okay? So, number one, everything can do dispersion. And remember, London dispersion is the same thing, it's just a proper name. Okay? So dispersion is always one of the forces that something can do. So the next question you have to ask yourself, is it polar? Okay? If yes, you have dipole-dipole interactions. And the third question to ask, is there hydrogen bonded directly to oxygen, nitrogen, or fluorine? If yes, you have hydrogen bonding. Okay? So evaluating intermolecular forces, determining what forces a particular molecule has, is an important skill for this chapter. Okay, so let's do that a little bit. What is the strongest intermolecular force between carbon dioxide molecules? So if I have a whole bunch of carbon dioxide molecules, what are their intermolecular forces going to be? So dispersion forces, like I said, everything can do dispersion forces. Okay? But dispersion forces are the weakest ones, remember. Okay? So question 2 was to ask yourself, is this a polar molecule? And with carbon dioxide, you would take a look at the shape of it. It's linear. Right? So it's straight across. Right? It's like a stick or a piece of a rod of steel or something. And you would look at the individual bonds and you would see that the oxygen is more electronegative than the carbon is in both cases. But they're pulling directly away from each other. They're canceling each other out. Okay? So this one is non-polar. Okay? So dipole-dipole interactions are off the table. Third question, do you have any hydrogens bonded directly to an oxygen, nitrogen, or fluorine? Well, there's no hydrogens in this molecule at all, so that's an easy peasy. And in order to have ionic forces, you need to have an ion, Do we have any ions? The answer is no. So the only thing that carbon dioxide can do is London dispersion. Okay? So all it's got is one weak force. So this gives an indication of why carbon dioxide is a gas, okay, at room temperature, because it has weak forces. There's nothing holding the individual carbon dioxide molecules together. Okay? Look at our next example. Right? We've already been over this with dispersion forces. Everyone can do dispersion forces, so that's a possible answer. So now let's look and see if this thing is polar. Now we talked about it in the last chapter that carbon-hydrogen bonds are basically non-polar bonds. So this bond, and this bond are not doing anything. Okay? Carbon-chlorine bond, on the other hand, is pulling that way. Right? So we have a polar molecule. If you're polar, question number 2 says if you're polar, if yes, then you have dipole-dipole interactions. Do we have a hydrogen bonded directly to an oxygen, nitrogen, or fluorine? The answer is no. And do we have any ions present? The answer is no. So between London dispersion and dipole-dipole interactions, dipole-dipole wins. Right? So, dispersion forces, always an answer. Right? Is it polar? That's question number 2. So these carbon-hydrogen bonds are basically doing nothing. I do, however, have a pull with the oxygen. Okay, so there's nothing canceling out that oxygen pull, so this is a polar molecule. Right? So dipole-dipole interactions are possible. Do we have a hydrogen bonded directly to an oxygen, nitrogen, or fluorine? And the answer is yes. So hydrogen bonding is possible. Do we have any ions? No. Ionic forces are out. So dispersion is the weakest, then dipole-dipole is the next strongest. Hydrogen bonding is the strongest of the 3. There we are. All right, so hopefully this is a gimme. This is a no-brainer. How many of the following molecules experience London dispersion? Everything experiences dispersion forces, so all of these molecules fit that category. Don't even have to look at the structures or what they're made of or anything. Everything can do dispersion. So how many of the following molecules experience hydrogen bonding? Okay, so in order to have hydrogen bonding, we have to have hydrogen bonded directly to an oxygen, nitrogen, or fluorine. So we can immediately cancel out anything that doesn't have those 3 elements. No oxygen, nitrogen, or fluorine. No there. No there. So let's look at this guy. So this molecule looks like this. Okay? So do we have our criteria for hydrogen bonding? And the answer is yes. Okay? And then ammonia. That's supposed to be an H. Right? Hydrogen bonded directly to oxygen, nitrogen, or fluorine. So we have 2 compounds here that can do hydrogen bonding.